In section 9.4 of chapter 9, we see an important application of solution calculations to solution stoichiometry, reactions where one or more reactant is present dissolved in solution. If you know the molarity of the solution and the volume in liters of the solution, you can calculate the moles of solute present, and then you can segue into a stoichiometry calculation for a reaction occurring in solution. Remember that you must have a balanced equation to do any type of stoichiometry problem, because the balanced equation gives you the coefficients needed in the mole-to-mole ratio involved in the stoichiometry calculation. Let's illustrate that with this first problem. What volume in milliliters of a 0.275 molar iron 3 chloride solution is required to react with 45 milliliters of a 0.350 molar solution of potassium hydroxide? So we have iron 3 chloride reacting with potassium hydroxide in solution. Both of these reactants are present, dissolved in solution. Here is the balanced equation for the reaction. Iron 3 chloride plus 3 moles of potassium hydroxide react to form a precipitate, a solid, iron 3 hydroxide, plus 3 moles of potassium chloride. Notice that I have taken the data in the problem and labeled it, listed it below each one of the reactants that it pertains to. So we need to calculate the volume in milliliters of our iron 3 chloride solution. That's what we're trying to solve for. The molarity of the iron 3 chloride is 0.275 molar, and notice that I have written that molarity as a conversion factor. 0.275 moles of iron 3 chloride per liter of solution. We have 45 milliliters of our potassium hydroxide solution involved in the reaction, and I have taken the molarity of the potassium hydroxide and written it as a conversion factor as well. 0.350 moles of potassium hydroxide per liter of solution. So what's our solution map, our path towards solving this problem? Well, if you have a molarity and a volume of a solution, you can calculate the moles of solute present. So we're able to take the molarity, convert the volume into liters, and calculate moles of potassium hydroxide. We are then able to use the mole-to-mole relationship from the balanced equation. 1 mole of iron 3 chloride reacts with 3 moles of potassium hydroxide to calculate moles of iron 3 chloride. This step right here is the stoichiometry of the problem. And then once we have moles of iron 3 chloride, we can use the molarity of the iron 3 chloride as a conversion factor to calculate the volume of iron 3 chloride solution needed. So let's arrange the data and use the conversion factors as illustrated in the solution map. Here is our volume of potassium hydroxide solution, the 45 milliliters, and I am converting that into liters of solution using the relationship 1 liter is equivalent to 1,000 milliliters. Once I have volume of potassium hydroxide solution in liters, I can now use the molarity of the potassium hydroxide as a conversion factor to solve for moles of potassium hydroxide. So right here, looking at the dimensional analysis, the milliliters of potassium hydroxide solution are canceling, the liters of potassium hydroxide solution are canceling, and I am left with moles of potassium hydroxide. I'm now ready to do the stoichiometry. I'm ready to take the mole-to-mole relationship from the balanced equation. 1 mole of iron 3 chloride reacts with 3 moles of potassium hydroxide. So multiplying by this mole-to-mole relationship, the moles of potassium hydroxide cancel, and I am left with moles of iron 3 chloride. I'm trying to calculate volume of iron 3 chloride solution needed. The iron 3 chloride is dissolved in water to make a solution. So I am going to take the molarity of the iron 3 chloride solution and use it in its inverted form as a conversion factor. There's an understood 1 liter in the denominator, so flipping this molarity, I have 1 liter of iron 3 chloride solution containing 0.275 moles of iron 3 chloride. My moles of iron 3 chloride are canceling in the calculation, and I am left with liters of iron 3 chloride solution. But the problem asked for us to calculate the volume in milliliters. So it's one final step in the setup, converting from liters of iron 3 chloride into milliliters of iron 3 chloride solution using the relationship 1,000 milliliters is equivalent to 1 liter. Stopping and checking our answer to make sure we confirm the calculation. It helps to be fast on a calculator and accurate. And double checking my answer, I see my setup has 3 sig figs as the minimum number of sig figs involved. So my answer expressed with 3 sig figs is 19.1 milliliters of iron 3 chloride solution. This first example is a straightforward stoichiometry calculation. I'd now like to illustrate a more complicated stoichiometry problem that involves knowledge of how to use mass amounts in stoichiometry, how to use gaseous ideal gas law data in stoichiometry, so gas stoichiometry, and solution stoichiometry. So involving all 3 types of stoichiometry that we have looked at so far. And this second problem illustrates that. If 0.5 grams of potassium sulfide reacts with 25 milliliters of 0.280 molar hydrochloric acid solution, what volume in milliliters of hydrogen sulfide gas will be produced at 30 degrees Celsius and 745 torr? So I see here that this problem involves a mass amount of potassium sulfide. It involves a molarity and a volume of hydrochloric acid, so solution stoichiometry in this part of the problem. And last, our product is a gas, and we are asked to calculate the volume of the gas given information about its temperature and pressure. So gas law stoichiometry involved also. All stoichiometry problems, we begin with a balanced equation. So potassium sulfide solid is reacting with hydrochloric acid in solution to give you hydrogen sulfide gas and potassium chloride as your other product. Balancing the equation, we have 2 moles of hydrochloric acid reacting with 1 mole of potassium sulfide, and we make 1 mole of hydrogen sulfide and 2 moles of potassium chloride. I've taken the information in the problem and labeled it below its appropriate substance in the equation. So 0.5 grams of potassium sulfide is given. We are given 25 milliliters of hydrochloric acid solution with a molarity of 0.280 molar. And notice I'm writing that molarity as a conversion factor. We are asked to calculate the volume of hydrogen sulfide in milliliters. Temperature is 30 degrees Celsius. Immediately converting that into Kelvin, 303 Kelvin. Pressure of hydrogen sulfide is 745 torr. Notice that in order to calculate the volume of hydrogen sulfide, we will also need to know the moles of hydrogen sulfide produced, and we are going to get that from a limiting reactant comparison of the data that has been provided for our two reactants. So if we know that we have 0.5 grams of potassium sulfide, we can use the molar mass of potassium sulfide and convert to moles of potassium sulfide. We can then use the mole-to-mole relationship in the problem 1-to-1 to find how many moles of hydrogen sulfide gas will be produced from our 0.5 grams of potassium sulfide. So looking at this calculation, our grams of potassium sulfide are canceling, our moles of potassium sulfide is canceling, and we are calculating moles of hydrogen sulfide. So double checking that calculation, I get 0.00453 moles of hydrogen sulfide gas produced. Now the temptation here would be to stop and use this mole amount of hydrogen sulfide to do the gas law calculation, but this is a limiting reactant stoichiometry problem. So we have to do a limiting reactant comparison to determine the mole amount of hydrogen sulfide, meaning we have to take the volume and molarity of hydrochloric acid, find out how many moles of hydrochloric acid we have, and then do a stoichiometry calculation to see how many moles of hydrogen sulfide would be produced from our hydrochloric acid reactant. Maybe it's the limiting reactant. Maybe the hydrochloric acid runs out first and we can't make this mole amount of hydrogen sulfide because we don't have enough hydrochloric acid to react with the potassium sulfide. So here is my second calculation involved in the limiting reactant comparison. I'm taking the 25 mils of hydrochloric acid solution, I'm converting it to liters, and then I'm using the molarity as a conversion factor to calculate moles of hydrochloric acid. Here comes the stoichiometry. 1 mole of hydrogen sulfide is produced for every 2 moles of hydrogen chloride that react. And let's just double check this answer and make sure we confirm what is written on the board. And double checking, I get 0.00350 moles of hydrogen sulfide that can be produced by the reaction of the volume and molarity of HCl provided. I'm ready to make the comparison, and as I look at these 2 mole amounts of hydrogen sulfide that can be produced from each reactant, I see that the smaller mole amount is 0.00350 moles of hydrogen sulfide. What that means is that HCl is the limiting reactant. It is making the smaller mole amount of hydrogen sulfide. So I can come here and write in 0.00350 moles of hydrogen sulfide is produced in this reaction. I now have a temperature, a pressure, and a mole amount of hydrogen sulfide. I should be able to do an ideal gas law calculation and find the volume of hydrogen sulfide produced in this reaction. So this brings us to our second step. Use the ideal gas law to calculate the volume of hydrogen sulfide produced. PV equals nRT is the ideal gas law, and we are solving this equation for volume, dividing both sides of the equation by pressure. This gives us volume equals nRT over P, and now we are coming and doing our plug and chug step of the calculation. Taking the data that has been listed, plugging it into the equation, and chugging through to calculate our answer. Our mole amount is 0.00350 moles of hydrogen sulfide. We just determined that mole amount from our limiting reactant comparison. We remember that our R value, if our pressure is in either torr or millimeters of mercury, the R value is 62.4 liter torr per mole Kelvin. Temperature is 303 Kelvin, and our pressure in the denominator is 745 torr. So we are ready to chug through the calculation and confirm our answer. And when I do this calculation, I am confirming that the volume is 0.0888 liters of hydrogen sulfide gas. One last detail to the problem. The A is always in the details. We were asked to solve for milliliters of hydrogen sulfide gas, and according to the dimensional analysis, when we look at our units, our moles canceling, our Kelvin canceling, our torr canceling, we are left with a volume in liters, not milliliters. So the very last step of the problem is to take our volume of 0.0888 liters, multiply by 1,000 milliliters per 1 liter, and our final answer for the volume of hydrogen sulfide produced is 88.8 milliliters.